So new day, so new topic. In organic chemistry today, we're going to be talking about analytical topics. Analytical techniques. And one of the most important analytical techniques is gas chromatography and mass spectroscopy. And together they're called gas chromatography, mass spectroscopy, so GCMS. So what is GCMS? Let's draw a simple diagram of gas chromatography. Gas chromatography is when you have a sample of some kind of gas that, let's say, you put through a syringe over here, and you put through a tube over here, and you push the gas towards this direction with some kind of inert gas that is connected here. Maybe it's some argon, it's probably argon, and then or nitrogen, and you're pushing the air towards the pipe, and at the end of the pipe you're gonna have some kind of detector like this. This is the detector, this is the gas syringe, and that's the inlet. This is the inert gas. Now, what does it look like inside the tube? Well, the whole point of doing gas chromatography is for us to know what the gas is made of. So inside this tube, we have this kind of shape, let's say. There's a couple of different shapes this can take. It can take something called a W-cut shape. And a W-cut shape is when it's just all liquid. Liquid is coated over here. There's also something called a S-cut, and that is a solid center that is covered with liquid. So it would look like having a solid center, but then being covered with liquid inside. That's going to be S-cut. And lastly, the P-lot, P-L-O-T, is the solid one, where just all the tube in its entirety is made out of the solid marbles. But whether it's plot-scot or W-cut, it's important what solvent you use. You might be using a non-polar one or a polar one, and that is really important depending on what your sample is from your inlet. So an example of a polar solvent would be PEG. An example of a non-polar one might be PPMS. So what happens if I coat some kind of polar substance over here, and then I insert a sample of a polar substance? Well, it's going to stick to the tubing. So guess what's going to happen? On the spectroscopy, on the detection, the early results are going to consist of the non-polar particles that might have been in the sample, and the later ones will be the polar one, because the polar ones would have a harder time being freed up by the inert gas because it's stuck to the sides of the pipe, because it's attracted to the polar surface of this tubing. So that's the gas chromatography. But gas chromatography is often used in tandem with the mass spectroscopy. There's different ways of mass spectroscopy too. So mass spectroscopy is basically used to find out the mass to charge ratio. And by that, you can find out the different compounds that are within it. Not just the non-polar versus polar, but because gas chromatography is basically used to separate non-polar and polar substances. Now, mass spectroscopy is more so finding out what each of those substances are. There's two main techniques I would like to compare. There's something called electron impact, also known as EI, and there's also electron spray, also known as ES. So there's one called electron impact over here, and there's also something called electron spray, like that. And I'll talk a bit more about which one is a bit more effective, but electron impact basically goes like, you have the substance over here, and you basically just bombard it with ejected electrons. You have some kind of hot filament here that gives off some kind of radiation. And because of this radiation, it ionizes the electrons. It excites the electrons in the substance, and the electrons are ejected outwards, like this. And when this happens, these fragments all hit the detector at different, with different masses. So they all have this all have the same charge, but they hit with different masses. So depending on that, you keep the charge constant. So the mass to charge ratio differs by checking the mass on the detector, where the charges stayed constant. So if its mass to charge ratio is equal to 1, then it's equal to the original substance. But if it's greater, it might be an isotope. That is how you would use an electron impact. And here is how you would use the ES, or electron spray. Electron spray is essentially when you have your solvent, your sample, and then in your sample, you basically spray a bunch of acid particles, a bunch of proton donating particles. So it's very positive. It coats the sample like this. And the sample is connected on the other side to a huge anode, and the detector is over here. Such that this positive is now attracted to here, but as it travels, it becomes smaller and smaller and smaller, and since the curvature, the radius of curvature decreases, the field that it is impacted by the field further, and that is shown by the constant of the relationship of E over R. And as it gets closer to the anode, it's further attracted to the anode, such that it gets swept into the detector faster. So depending on that, the amount of substance, or which substance reaches the detector first, is dependent on the mass and how fast these particles can travel. That's the electron spray. So I want to give an example of such an example, and we can look at this example over here. This is an example of one of the mass spectroscopy results, and you can see that, actually, let's look at this one. This is one of the mass spectroscopy results. You can see that here, M-17. This is the original molecule that came in, but there is a huge M-17 here. That happens when there's fragmentation. So when using ES, electron spray method, the molecules can get ejected. So once it's coated by protons, as it moves, the proton and the middle parts can get closer together and eject molecules in the process. So there might be some lost molecules that show up on the spectroscopy here. So the original sample is supposed to be 390 in terms of mass to charge ratio. That's supposed to be right around here. So that's 391, and that's the original M plus H phase, but then here there's an M-17 and there's a small peak over here, and that's because it lost an NH3 ligand from this molecule over here, and because it lost the NH3 ligand, since the molar mass of this amine is N plus H, which is 14 plus 1 plus 1 plus 1, which is equal to 17. That's why it's named M-17 over here. That's why there's a peak over here. So you can see all of these separated masses, all of these separated substances, based on the amount of mass they lose when they transfer over their mass to charge ratio. So the more they lose, the more mass to charge the mass to charge ratio is going to get smaller and smaller and smaller. So the more things that they start to lose as the ionization energy or impact gets stronger, the more particles they're going to start to leave behind, and that's how you see the spread out composition. Now the second technique that I really want to talk about is NMR. It's nuclear magnetic resonance. So as you might guess, it uses a gigantic magnet to do its analysis, NMR. And basically NMR spec is seen as really complicated, but it's really simple. It's basically putting a huge magnet, pursuing some kind of external magnetic field of B, and you have the substance in the middle, right? And this substance has this substance must only have an odd number of electrons, and this is because if not an odd number of electrons, then the valence shell is going to look something like this, where it's paired up, and it will not have a net spin. If it has a net spin, it's going to have some kind of magnetic field of its own, which is why it's paramagnetic. It can align. It can be its own little magnet, but if it's canceled out, the overall spin is zero, because one electron has a half spin and the other must have the opposite and equal spin. So this would equal to zero. But if only one is present, there is a net spin, whichever one it might be. And so it can interact with the magnet. Now, what we want to do is we want to we want to give it some radio frequency, some RF frequency, such that this molecule emits the amount of radio frequency that it absorbed. And the amount that it absorbs depends on the electron density. So if the electron density of the molecule is high, then it means that it has a stronger local magnetic field, so it's going to be able to absorb much more. So if it's absorbing much more, then it's going to have a downshift in terms of the NMR. And if it has less of an electron density, then it has a weaker local magnetic field. So it's going to be easier to align this stubborn magnet in the way of the external magnetic field. So there's going to be an upshift, meaning that it's going to be easier for this for the radio frequency, for the amount of radio frequency emitted to come out. So there's going to be an increase in frequency because it will spit out less radio frequency. It will spit out more radio frequency because it absorbed less. So just to recap, if it has more electron density, then it will have a downshift because it absorbs more radio frequency and therefore it emits less. If it has more electron density, then it has less of a stubborn magnetic field, so it aligns more easily, so it requires less radio frequency, therefore it absorbs less and emits more, so there's an upshift. Now, what's a very important effect to know? There's something called spin-spin coupling. So this depends on the environment, and this is where things get a little bit tricky. So environments depend on the type of NMR you're doing. There's different types of NMRs. You can do them with 1H NMR, or you can do it with you can also do it with carbon-13 NMR. You can also do it with fluorine-19 NMR. There's different NMRs out there, but obviously all with the odd numbers of electrons. But the environment is basically dependent on what kind of NMR it is. Let's look at the hydrogen NMR because it's one of the most common ones, and let's look at some kind of molecule where there's a hydrogen here, and the same kind of hydrogen over here, like that, like this, and like this. So this is one environment because this one environment is defined by some kind of distinguishable carbon that is connected to a proton. So this carbon is connected to this specific proton. This carbon is connected to this specific proton in a way that their environment differs. If it was X, Y, then this would be the exact same carbon environment. So then it would just be one environment. But since it's not, there are two distinct proton environments over here, the two distinct carbon environments, hydrogen environments. So we can say that there are two total distinct environments. And what happens if I give this molecule, this atom, a radio frequency, if I hit it with radio frequency? If this neighboring proton over here has some kind of aligned magnetic field, such that if the external field was in this direction, let's say that this spin was also in this direction overall, that means it contributes to the overall magnetic field. So now the whole molecule, this molecule, there's going to be a net stronger magnetic field, so it's going to take less energy for this to be flipped because the magnetic field applied against it is stronger. So less radio frequency is going to be needed, so more is going to be emitted, so there's going to be an upshift. On the other hand, if there's the opposite spin of the net magnetic direction, then the magnetic field applied is going to get weaker. So I'm going to need more radio frequency to flip this to match the external magnetic field. So there's going to be a downshift because more is going to be absorbed and so less is going to be emitted. So that is how that works. So then you might have heard of the N+1 rule. And the N+1 rule is quite simple if you consider the different cases that this might have. So if I'm talking about this hydrogen over here, let's say we're looking at this hydrogen over here of HA. And let's say that this hydrogen, if this is upshift, up spin, then there might be a case where both of these hydrogens in the other environment are downspins. And in this case, that's where there's going to be definitely there's definitely going to be a downshift because it's opposing. Let's say that this is the case, then this cancels out, so there's no effect, and it can be this as well. on the other hand. And then there can also be the fact that both of them are upshift, and in this case that's going to be upshift because they're both all in the same direction. So this is going to be downshift, this is going to be upshift, and this is going to have a net zero effect. So there's 3 total cases. So we can say n plus 1 is equal to 3. So n plus 1 is basically the total number of configurations that one environment can take. And here n is basically going to be equal to the number of protons. So n is equal to 2. And number of protons here, I mean by the number of protons in the adjacent environment. And what do you think about that? Here, if I see HA as a standard, in our neighboring environment, we do have 2 protons, 2 hydrogens. So this number is exactly correct. And in an NMR, it will show up as some kind of triplet or a singlet. For example, if it's n plus 1 is equal to 2, then n is equal to 1. If n plus 1 is equal to 1, then n is equal to 0. And when n is equal to 0, it's a singlet. When n is equal to 1, it's going to be a doublet, like this, or a triplet like this, and onwards until it gets to a multiplet, when it can have much more of the splitting over here. So that splitting tells you about the environment, that the neighboring environment, so you can guess what kind of structure it will end up having. So 2 very important things. You have to know about the number of protons in the general in your neighboring environment, and you also have to know about whether it's going to be downshift or upshift depending on the spin that it already possesses. So will it absorb more radio frequency or less radio frequency? You'll find that out by looking at the NMR target that you have and the molecules that you might potentially have on an NMR diagram. And you will look at both mass to charge ratio, and you will look at the intensity ratio. And here the intensity ratio is basically a ratio of the mass to charge ratio. And if you look at the mass to charge ratio, you will be able to guess based on the n plus 1 rule which environments are located in which environment. So you can do that question as well. So that is it for today.